Okay.
Okay, yeah. So if you remember with me yesterday, I sort of really write the result for black holes for how you define the mass of the black hole by looking at a localized matter distribution in the d dimensions. And then I found the leading order T00 contribution to the metric. So now I would like to generalize this to peak rings. First of all, I choose some coordinates for the flat space background that I'm going to study this in. So that's the ones I wrote here. Then I will define where my matter distribution is in this space-time. So I'm going to define some radius in terms of these y coordinates, which is this. And I think I also said yesterday that this n is defined as d minus 3. So, and then I'm going to say that the matter distribution is localized at r less than L. So you can say it's localized around the origin of this part of space-time. But instead, for this part, it can be everywhere. So this part here, this is the longitudinal part. So it's sort of longitudinal to the matter distribution. And this part here is transverse to the matter distribution. And again, we consider this matter distribution to be Newtonian or special relativistic matter in the sense that it only has a mild influence on the gravitational field. So if I should make, okay, just wait a second. Okay, so I want to generalize what I did yesterday to peak rings. I choose these coordinates for flat space. So this is the longitudinal to the matter distribution. This is transverse to the matter distribution. And then I'm looking at a matter distribution which is localized. So the radius, there's only matter for the radius being less than L. So it's localized in terms of the transverse part, but not the longitudinal one. And if I want to make a drawing of this, then it would look something like this. So down here we have the transverse coordinates. So we have L, and then the matter is localized within this strip. And then this way we have the longitudinal coordinates, and here the matter is not localized. So then you can ask again, what is the monopole moment? Because we again look at distances very far away. So this R coordinate only includes the transverse, not the longitudinal. So if R is very big, we go very much this way. Right? So if we are very far away from the matter distribution in this sense, then we can look at what are the leading contributions to the gravitational field. And this comes from the monopole moment, again, just like for what we had yesterday. But now, since we have these longitudinal directions, the monopole moment is more complicated. Because the monopole moment, instead of only including the time component of G mu nu, it includes all the G mu nu components along the longitudinal direction. So all the directions from 0 to p. And we measure this in analogy with the mass as the integral over the energy momentum tensor in these directions. And then this is this is the thing integrated, and this is what corresponds to the mass for the black hole case. But here is something we call a stress tensor. Sort of in an analogy with the solids. So how should you understand that? Well, actually, if you do this thing of integrating out the length scale L here, so you sort of send L to 0, and you only keep the monopole moment of the matter distribution now. So this is like an approximation to the matter distribution. Then you can see that what is left then is that the energy momentum tensor is given only by this stress tensor times the delta function. So this is again a p from 0, 1 to p, and then G mu nu is 0 otherwise. I mean, all the other components are 0. So we have a delta function, but it's a delta function only in the transverse space. So what this corresponds to is a infinitely thin p-brane, and this is the higher dimensional generalization of a point particle. So if we should draw a picture, sort of in analogy with the picture over there, what should we draw? Well, we should draw just a line now, because now the matter distribution is simply localized on this line as the origin of the transverse space. And this is how we define what we mean with a p-brane, right? And this p-brane then has this stress tensor, which is defined in this way from the original matter distribution. So any questions to this part? So it's clear, more or less. Okay, so now we will again analyze the gravitational field from this. So we again look at this perturbation of Minkowski space. And now we assume that this perturbation doesn't depend on the longitudinal part, because then we can write the Einstein equations, and this is, I mean, from what we knew yesterday, pretty easy to see. So I'm not going to repeat that. But now nonetheless squared is different from yesterday, because the transfer space is different. So it only includes the directions from the n plus 2 directions instead of e minus 1 directions as we had yesterday. And for that reason, when we integrate it, or when we solve this differential equation, the solution is going to look slightly different. Well, very similar. So the solution is simply this. Is this. And then if we look at the components along the world volume, the longitudinal components. So when I say the world volume, I really mean the directions along the peak brain. So I'll probably say that again. So if you look at the longitudinal directions of H, we get this. And then we insert now, I think I deleted that, but we insert now the TAD in terms of the space tensor, which was this. So I insert this in the C mu nu, right? Then we only get a contribution when y prime here is 0, because that's where the delta function sits. So it all this becomes the radial coordinate to the n. And then here we just have to insert the stress tensor, because we then have an integral over the stress tensor. So altogether, it becomes this. So now we have the analogy of the formula for the black hole, or the localized matter distribution. namely we have how the gravitational field should look for a given stress tensor. And this we can now use to define the stress tensor of black P branes in analogy with Newtonian or special relativistic matter that sits at a P brane geometry. But I'm going to make one more assumption, namely I'm going to assume something about the form of this stress tensor. Maybe I'll put it here. So I will assume, and this is because it's going to turn out to be true for most branes that we will look at. All the branes we will look at, but it's also true for most branes that one can't look at. I'm going to assume that the stress tensor is of perfect fluid form. And this is, there's a very, I cannot tell you the whole story here because I haven't introduced you to all the concepts, but there's something, in the end we'll sort of find out that in general a brane on its wall volume behaves a bit like a fluid, but if you sort of bend the brane or do things like that in the transverse directions, it behaves more like a solid. So it's sort of both fluid and a solid at the same time. So I'm going to throw names that indicate both fluids and solids in this sense. But anyway, so here I will use fluid dynamic concepts. So this is a perfect fluid form, and epsilon here is the energy density of the fluid. And P is the pressure, and this P is big P, whereas P of the P brane is small p. It's hard to tell the difference. Sorry for that. So P is the pressure of the fluid, and this UA is the fluid velocity. And as any velocity, you have that the norm is -1. So if we insert this perfect fluid form for the stress tensor here, we can write that HAB is equal to the same thing here, and then this thing. I hope it's readable. So epsilon plus P, UA, UB, epsilon plus N plus 1 times P over D minus 2, and then eta AB. So this is what I will now use to measure the stress tensor of black branes, this formula. So if you take now, the black P brane, then we want to measure, then we want to look at how does this influence the gravitational field far away from the event horizon radius, right? And if you remember, the metric looks like this. Okay, so yeah, maybe I'll write it like that. I changed the name of the longitudinal coordinates from what I had before. Anyway, so we have this as the metric, and then we can read off from this part here. So if I call T sigma 0, right? Then we can read off from this part here what is the energy density, the pressure, and the fluid velocity. So first of all, you see that there's no mixed components with time. So the fluid velocity is just 0 with the 1 in the time direction, of course. Then you also see that the components, the special longitudinal components, doesn't get any contribution. So if you look at this formula, so this doesn't go. This is not there in the special directions. There's only this part here. So then you see that epsilon plus n plus 1p has to be 0. So this actually gives us an equation of state for what we can call the fluid living on this pea brain, black pea brain. So this is an equation of state because it relates the pressure to the energy. Then we can read off that if we now look at the time component, then we have a contribution both from here and here. You end up with something like this if you use the equation of state as well. So this R0n is this R0n here. And then you can write off what the energy density and pressure of the fluid are. So you see here that the pressure is negative. So it's not what you normally would think is possible for a fluid, right? So it's kind of a different type of fluid than you're used to. But there's a reason that it's negative, and that's because there's another way. If you go more in the terminology of solids, then you can think of the brain as having a tension, just like the string tension in string theory. And the tension is equal to the minus the pressure. And this tension is positive. And then it has to be so. The tension is a little bit like the tension of an elastic band, right? That if you try to stretch it, then there's a force trying to pull it together. And that means it has a positive tension. And in the same way, this also these branes also have a positive tension. Okay. So all this is what is analogous to the mass of a black hole. So you see, black P-branes has a lot more information than the black hole, right? Because all this is analogous to the mass. But then we have some other quantities as well, just like we had for the black hole. So I'm going to explain how you measure those, because it works exactly the same way as for black holes. There's no surprises there. So you have a Hawking temperature, just like we had for black holes. So now the Hawking temperature for black neutral black P-branes is given by this.
Sorry?
Yeah.
What's the condition for the last equation over there? I mean, where does it come from? Yeah, that one.
This one.
Uh-huh.
Yeah, now I just deleted it, unfortunately. But so you had HAB equal to there's some constants here. So you can see that this doesn't contribute in the spatial directions, right?
Yeah,
because
the choice
the velocity is static.
Okay.
Or zero, right?
Mm-hmm.
So there's only a contribution from this. And then you see that this has to be zero, because HAB is zero in the spatial directions. You know, if you write the metric here, it's just say GAA equal to 1, right? For A from 1 to P. So that means that there's no correction in these, there's no correction to the Minkowski metric in these directions, right? So it means that in those directions, HAA is equal to 0. Is this clear?
Yeah.
Because otherwise, this is more or less clear. I mean, instead here, I can put the minus. Instead here, there is a correction to the Minkowski part, because here you have G00 is minus 1 plus R0 to the n over R0 again. And this means that, you know, this is the Minkowski part, of course. So H00 must be R0 to the n over Rn, right? So instead here there is a correction. And that's the correction you pick up if you set A and B equal to 0 in this formula, right? Then you have both the contribution from this term and from that term, right? Except, of course, now that since you derived it from the other components that epsilon plus n plus 1 plus times p is 0, then this is just identically 0 for that reason. So it's then you basically end up with only this epsilon plus p here, since then UA UB is 1. Right? And that's how I find this from the 0, 0.
Thank you.
How did you read the UA?
Well, that's just if you see if UA was different from 0, then in particular you would have a component U0, U0, UA, where A is, well, U0, U1, for example, you would have, right? If you say that U1 is different from 0. And this is a mixed component with time and space. But in this metric, there's no mixed components with time and space. So therefore, all of these has to be 0, right? And then the 1 I'm simply getting from, you know, that U squared has to be, the norm of the velocity has to be -1. So that normalizes this to be 1.
This is just the rest frame of the fluid, right?
Yes. Yes.
So this seems inconsistent if you're not in that frame.
Well, I'm just reading off for this particular metric what fluid it corresponds to. I'll have a comment in a moment about that. So maybe let me come back to that. Yeah, so maybe I went a bit too fast when reading off this, but it really works exactly the same way as yesterday for the black hole. I mean, you just insert, you just look at the 1 over r to the n correction to the metric compared to Minkowski space, and then use this formula, and then you get these results. Okay, so you have a Hawking temperature, then you have an entropy density, so now it's a density because it's the entropy per volume element of the p-brane volume. And then you have a first law of thermodynamics, which means that the energy density, the variation of the energy density is equal to the temperature times the variation of the entropy density. And then you also have a relation, you can just check if you insert this and these expressions here, you have this relation here. And this is known in thermodynamics as the Euler-Gibbs-Duhem equation. So it's something you find some standard result in thermodynamics that it looks like. But yeah, so let me come back to this point with rest frame, because so what I mean, let's take this metric here. And then imagine that we boost, we make a boost along some of the longitudinal directions. So we have some sort of Lorentz transformation, say something like this. Where this is a constant matrix. So you make some Lorentz transformation in the longitudinal directions. So what happens to the what happens to the metric is well, let me define now UA to be UA to be this in terms of the of this matrix. Then I can write the resulting boosted black p-brane metric which is just a boosted version of the metric over there, as the following. So I won't put primes here, but there's a hidden prime in these coordinates. You can say. So this is what you call a boosted black P-grain, boosted along the work. And now, if you wanted to, now you could again play this game of reading of, you know, using this formula H, A, B equals something, epsilon plus P, UA, UB plus epsilon plus N plus 1, P, E minus 2, A, B. You could again play this game of reading of the 1 over R to the N correction, right? So the R to the N to the Minkowski. Maybe I should write it again just to speak. I guess it's N omega N plus 160 pi G R to the N. So now you could again play this game of reading of the 1 over R to the N correction. But now for this metric instead. So you see that the correction means the longitudinal directions are this, of course, right? So, and this is the Minkowski metric. So the correction is this part, right? So if you look at this and you compare to this over here, you see that that must mean that this UA I defined here is nothing but the fluid velocity. Okay? And then this thing here must be 16, N omega N plus 1 over 16 pi G epsilon plus P over R to the N. Then UA, right? And that part here has to be 0. So in the end, you get the same function of state, you get the same energy density and pressure, but now you get a different fluid velocity. So it's not a fluid at rest anymore, but it has a constant velocity. And in terms of this Lorentz transformation, this is the velocity. Well, it just means that you have an arbitrary velocity where the norm of this u has to square to minus 1. So this defines your the sort of analog perfect fluid that corresponds to a black P-grain.
But is it a new solution? It's not a new solution.
Which one? This one here?
Yeah.
Well, it's a different metric than that one.
But what you only do is a Lorentz transformation. No?
Yeah, so sorry. I mean, I didn't do anything profound. No, I mean.
No, but then it's gauge transformation. What you do is just coordinate transformation of some coordinates.
Yeah, I mean, it's you can call it what you want. I mean, it's sure, it's a coordinate transformation. Yeah. But you know, that's the same for the fluid, right? Like if you have a perfect fluid. Now I didn't write it. So it's not on the blackboard anymore. But if you have this perfect fluid. Stress tensor, right? Then, you know, you can also boost that, right? And then whether you want to call that a gauge transformation, I don't know. It's a coordinate transformation.
I mean, it's a new solution or not? I mean, this metric is relates to the previous one up to a diffeomorphism.
Yeah. So I mean, seen from GR, it's not a new solution, sure. From general relativity point of view, this and that are exactly the same. It's just expressed in different coordinates. But you know, that's also how you see special relativity. That you know, all frames are equivalent. It's just do Lorentz transformations. So, yeah. Okay. So that is sure. That is true. Okay. So now I hope this will not confuse you more than necessary. But for later use, I just want to have a small interlude on other types of brains, because here I've been talking only about neutral black pea brains. But you could also talk about other types of brains. For example, you could look at what is called black DP brains, or non-extremal DP brains in general. This gives then, so this is of course in string theory, and we have 10 dimensions, so this is a very specific case, although I keep P general. And then we can consider the metric in the Einstein frame for such brains. And it looks like this. And here n is t minus p minus 3, but then since t is 10, this is 7 minus p. Okay? And then you have the harmonic function, which comes from the charge of the DP brane. And then you have the same sort of non-extremal harmonic function, which comes from having the event horizon. So this is the metric for n coincident DP branes, non-extremal. And you can also relate the number n of DP branes to these quantities that I used here, so sorry for being in the way. So I'll not say why this is and all that. I'll just say that this is how it is, and then you have to believe me. So this relates you the number n of branes to the R0 and alpha parameters. And then, so you have two parameters, R0 and alpha, right? And here there's one physical parameter, so then we can take the other physical parameter to be the temperature, and the temperature is then N over 4 pi R0 push alpha. So then in principle you can write up R0 in terms of T and N and alpha in terms of T and N by inverted by solving for these here. Okay, and then fortunately I didn't delete it this time. We still have we can do the same game using the same result and read off and I mean it's also a perfect fluid in this case, and then we can read off the energy density and the pressure, and again this is in the static frame, so the fluid velocity is 0, and
here T dP is the tension.
T
dP.
Yeah, sorry, yeah, this is the tension of a dP brane. Yeah, there's some specific formula in terms of, you know, the string length and string coupling and all that. So I'll just write what H is, since maybe that also makes what I did before slightly clearer. So now I write what the perturbation to Minkowski space is for this metric. In the time direction, it's this, which you should be able to read off directly from this, right? I hope. And the special directions along the world volume, I mean, special longitudinal directions, it's that. And then after some manipulations and a little algebra, not too complicated, you can read out what the. Sorry, 1 second. So you can read out what the energy density and the pressure are. So let me write this. So this is the energy density and pressure in the perfect fluid analogy of the black dP brane. And if you set alpha to 0, you see that you just get the result for the neutral black dP branes that we looked at before, and of course this metric. You know, that corresponds to setting n equals 0. So that's it. Sorry, there was a question, maybe.
Yeah, these H factors that arise in the metric now are because of the brain is subject to boundary conditions, or that's nothing?
Well, no, it's because now I'm not solving Einstein, pure Einstein gravity anymore. So you have to include the dilaton, you have to include higher form higher form field strength and things like that to find this metric. I will not talk about that. I will just sort of take the result of all those things, and then you have that metric. I mean, it's more to show that also for those types of brains, wherever they come from, you know, I don't really care how this all lands in equations in some sense. So I just take the brain and then see, that is the analog fluid.
Just about this H, isn't it power of minus n power of 8 is?
Yes.
But why we don't have this in H00 such stuff?
Why I don't have what?
So in collection, our collection.
Because the H is 1 minus something.
Yeah,
Just
yeah.
expanding the H. So the 1 minus plus something to the minus n over 8 just gives you 1 minus n over 8 times that something.
Yeah, but the last one again should have that power is n over 8.
You mean this one? Or what?
The sign should have such.
I mean, there's a minus 1 in front here that I think you're forgetting maybe. So anyway, I mean, this is true. So you should just work it out for yourself. I will not do it.
And alpha here is alpha prime.
No, alpha here is a parameter which is related to the charge in this way. Alpha prime sits in this tension. There's no relation between alpha and alpha. Okay, so I don't want to spend more time on explaining why that is the metric of the T brain, because that is not really the subject of my talk. So for that, you know, ask me after the lecture or something, maybe I can explain it. But now instead I want to turn to what's the significance of all this. So what can we use all this for? Yeah. So we again go back to the black hole case, which corresponds to P equals 0. And then what have we learned? What we have learned that far away which means R greater than R0, we can treat the black hole as a point particle of mass m. And then there was some specific formula, say for 4D it was R0 over 2D. I don't remember the general one. So we can treat it as a point particle of a certain mass to leading order, as a leading order approximation to a black hole if we're far away from a black hole. So that's something we learned. But suppose now we want to insert this black hole in a background geometry. And suppose that this has metric G mu. And it's d-dimensional, just to be general. D-dimensional spacetime, this metric. Then I have to explain how I want to do this, because normally that wouldn't really be possible. But suppose that by R I mean the minimum, well, maybe I don't have to put it in quotes, the minimum length scale that you find in this metric, in the sense that say if you are at some point in this space-time and you go to a local Minkowski frame, so where the metric, you change coordinates so the metric is the Minkowski metric, then how far away from that point do you have to go before the metric starts deviating from the Minkowski metric? You know, what is the typical length scale of that? And I will call the minimum of those length scales R. I mean, there can of course be even bigger length scales, but that doesn't matter to me. So this is the typical length scale over which this metric changes. Okay. And then you see that if now I take R to be much greater than R0, then locally in this space-time, I can go to this Minkowski frame, I can put in my black hole and treat it as a point particle, because the metric to a good approximation is just the Minkowski metric. And in this way, I can find a way to approximately understand how black holes behave in a more general space-time. I just have to be in this regime where the size of the black hole is much smaller than the length scale over which the background metric changes. And then this background metric can be whatever you want. It can be de Sitter, anti-de Sitter, Friedman, Robertson, Walker, whatever your favorite metric is. Or it could be another black hole background even. Anyway, so so then you can ask, what governs the dynamics of the black hole in this background geometry? Well, then we should just take the consequence of what we said here. We treat it as a point particle, hence we know how a point particle should behave in a geometry. It should follow the geodesic equation. So the geodesic equation is this. Where this x mu of tau is the position of the black hole in the background geometry. So the black hole simply travels along the geodesic in the space-time, because we can treat it as a point particle. And this Christoffel symbol here is just the Christoffel symbol of the background metric G mu, right? So, like we used to. Then you can, so what happens? This is an approximation, right? And this is an approximation that works in this regime here. And as all approximations, you have like a leading order, then you have first correction, second correction, so on. So what happens at higher orders in R0 over R. So if we take, how should we do this? And this is something called the match asymptotic expansion technique. Or MAE in short. So what one does is you first take into account how the black hole influence. You find correction to G mu nu from like a point particle source. Because of course a point particle will have this weak correction to the surrounding metric that we haven't included in the background metric. So you make this first correction, and then you use that what to say? This correction, you know how it looks in sort of an overlap region, which is far from the black hole, but still close enough for the geometry of G mu nu to look like Minkowski space. But then you want to take that as a boundary condition to find the corrected G mu nu metric all over space-time, far away from the black hole. So then you find the first order corrected metric G mu nu, the first order correction to the metric G mu nu everywhere in space-time, and doing that you have to now when you take that gives you some new corrections to the metric in this overlap region that you then can again use as input for some sort of boundary condition for the metric near the black hole, because it sort of gives you a correction, before the black hole was in a asymptotically flat space-time. Now the black hole will be in a non-asymptotically flat space-time because there's going to be some correction from this far away from the black hole, and this means that you should compute the correction to the geometry near the black hole. So this Schwarzschild-Tangolini metric that I wrote yesterday will be corrected. And then you can again see how this sources the background, and then compute a second correction to G mu nu, and then that gives you some new boundary condition for the metric near the black hole. So second correction to black hole geometry, and then in this way you can just keep going on, and you will find corrections to higher and higher order in R0 over R. Okay, so with this I take a 10-minute break. So till I guess 10:50. For the black hole, now we go to the black p-brane, so not the p-brane, but the black p-brane. So it's the neutral p-brane, and then we want to put a black p-brane in a background geometry. And then I say here that the minimum length scale should be bigger than this R, which is some length of the typical length scale. And then we have for R0, well, this R0 is now the event horizon radius of the black P brane. For this R0, much less than R. In analogy with what I just did, the dynamics of the black P brane to leading order. So leading order in R0 over R, the dynamics of the black P brane can be described by the dynamics of an infinitely thin P brane. So the dynamics of the infinitely thin P brane with same stress tensor. So this is to leading order in R0 over R. And then you can ask, what is the dynamics of an infinitely thin P brane corresponding to the geodesic equation we had before for a point particle? So first, you remember for the point particle, we had this world line, which tells you how the point particle world line is embedded in the background geometry. So we need the corresponding embedding for an infinitely thin P frame. And that is this thing here, where now the world volume coordinates are the P+1 longitudinal coordinates of the P frame. Okay? Generalizing this single coordinate for the particle. And then I also say that so this is called the embedding of the P brane in the background. Right? So the background geometry here.
I don't understand this thing about infinitely thin. I mean, P branes are infinitely thin. No, but is it, you mean that the event horizon can be seen as narrow, or the actual, because for example the black hole is thin,
but you should distinguish between two things here.
Yeah.
There's the geometry of the black P brane.
Yeah.
That is not infinite.
No,
there you don't have an infinitely thin brane.
Up to the horizon.
It has a thickness.
Okay.
Yeah. So I'm going to approximate that brane with a finite thickness with another P brane which is infinitely thin.
Yeah.
Right? So I'm like integrating out the scale of the thickness of the brane.
Yeah, I see.
Yeah. So I say over there that the minimum length scale of the background geometry should be bigger than R, and I also want that the embedding here should be such that the variation of the embedding so that the length scale of the variation of embedding should also be bigger than R. So I cannot describe something where the brane is bending over length scales which are very small, because I need this approximation scheme here. Yeah. Then what else do we need? We need the stress tensor. So this locally will be the stress tensor of a neutral black P grain. With the energy density and pressure that I wrote before. And then I need an analog of the geodesic equation, which somehow disappeared from my notes, but anyway. I think I can remember them. Let's see. Yeah. So the analog to the geodesic equation are those two equations that I will write now. So this last one is the direct analog to the geodesic equation. I hope you can see the analogy. But now you see, now it's more complicated simply because the embedding here is more complicated, right? It's not a word line. It is some sort of P plus one dimensional submanifold of a d-dimensional spacetime. But the form of the equation is the same. And this here is again the Christoffel symbol of the background, right? So this is only given by the background. Then you see you have some covariant derivatives here. This is the covariant derivative on the world volume. And why should that be a non-trivial derivative? Well, that's because on the world volume you actually have an induced metric from a non-trivial, if you have a non-trivial embedding. And in terms of the embedding and your background geometry, the induced metric on the brain, gamma AB, looks like that. So this covariant derivative is the covariant derivative with respect to this induced metric. Okay. So then I wrote two equations. So this equation is the intrinsic equation, the one I mentioned here. Sorry, maybe I said it wrong. The extrinsic equation for the brain. Then there's an intrinsic equation that also has an analog for the point particle, because this is nothing but the conservation law of the stress tensor. For the point particle, the analog would just be to say that the mass shouldn't vary in time. But that is sort of implicitly assumed in what we did, so we didn't write it. So this is the conservation of the stress tensor. And the claim is now that these two equations govern the full dynamics for any black GP brain in any background geometry, as long as you are in this regime. And before explaining a little more what this means, just want to write this equation in a different way because it's customary to define this tensor, or whatever you can call it, since it's sort of a mix of it, from world volume and background. But it's customary to define this object because this is a purely geometric object, which you can compute completely in terms of the embedding and background geometry. So it's a purely geometric object, and you call this the extrinsic curvature tensor. And then you can of course see that then you can write this equation like this, the extrinsic equation. And this is also known as the Carter equation. Carter was the first one that sort of formalized all this.
Sir?
Yeah.
I want to clarify what is the definition of big R, because big R was defined as the minimal dense scale. So it looks like the minimal dense scale is larger than the minimal dense scale.
Yeah, that's because, suppose you have the background geometry, so that has some minimum length scale, let's call it R1, okay? But then I also have the embedding, that also has some minimum length scale, because for example, I could take the embedding of a line in flat space, and then it could be at some curve, right? And then there's some typical length scale of the base of the curve, right? Like, for example, the radius of a circle, right? That gives me another typical length scale for the embedding. So I'm just saying here that I want that this R is less than both of these length scale. Because, I want in this regime that both the embedding looks trivial, completely like a line or completely flat, and the geometry, the background geometry should be trivial, in Minkowski space, if you have distances much smaller than R. So, but it's just because it's both the background geometry and the embedding that should look flat. So this finally brings me to something over here that is known as the blackfold approach to black holes. So what is a blackfold? Well, all of this means that we can take a black P-brane, we can choose some embedding, sigma, and some background geometry, and then we have to be in this regime again that I just explained, and then to leading order, the dynamics is described by these two equations. But then I said that the stress tensor then has to be the stress tensor of the black P brane. So here I have to insert that this is of perfect fluid form. And then notice that this is actually the induced metric here, not Minkowski metric, so it's more general now. That also means that UA, UB has to be minus, the norm has to be -1 with respect to the induced metric. And then I want to substitute in what that energy density should be the one we have had for the that we computed for the black P brane. And similarly the pressure. And then we have also some velocity. So what really happens here? Well, the reason, first of all, the reason why we call it a black fold is just short for a black P brane folded along this embedding. I mean, this submanifold given by the embedding in the background geometry. So you can imagine you're folding this brane along a specific embedding, and this embedding, like for a string, it could be a circle, for example, if you try, or some general curve that you want to fold this brane along. And the blackness part, that's the sort of folding part. The blackness part is that I'm specifically saying that I'm looking at a black P brane. So it's actually an object with an event horizon that, to a good approximation, I can describe in this way. So with these equations for the dynamics. Then everywhere on this submanifold, I have locally an energy density, and I have a pressure, and I have a velocity. But these three quantities don't have to be the same everywhere. They can vary on the submanifold. So that's why there's a dependency on the work volume direction. So what you sort of should imagine is that if you see this submanifold, sort of in general, it can be some curved submanifold, right? And then you can look locally on these submanifolds, locally on the submanifold, because of this approximation scheme, the brane looks flat and the background geometry looks flat. So locally, you can say we have a constant geometry. I mean, we have a constant we have a constant R0 and we have a constant what is the other thing? Yeah, I'm not sure there's any other. RU, yeah, velocity. And then suppose we, so all these are constant, and suppose we, because we are looking locally on the submanifold, so at distances smaller than r, so suppose we want to write the metric there, so the local metric near the brain, then it's a slight generalization of this boosted P-brain metric that I wrote before. So this is the metric you have if you are near the brain. And distances smaller than r, I mean distances along the world volume. So sort of you have some domains on the submanifold where you can approximately take these parameters to be constant, but then you have other domains, you know, where they have other values, and so on here. And then to sort of see the variation of going from here to here, you have to use these equations, right, for how you vary. But if you stay within one of these domains, then it's just a flat P-brain in Minkowski space. I hope that made it more clear and not more confusion. It's just another way to say that on this submanifold at small scales, you're just dealing with a black P-brain, just in slightly different coordinates than what I wrote before. At large scales, you're approximating that black P-brain to be an infinitely thin brain with the stress tensor given in terms of these quantities, and you use these equations. So these equations describe how all these things vary at distances of order r or larger. Okay? So this is an approximation, and this is something you can of course then go to higher orders. I will not describe again how this works, but it's completely analogous to what I said for the black hole case. Then what I just said is only true for these neutral black. Well, not all of it is specific to that, but there's some things you have to do, some extra things you have to do if you have to go beyond neutral, like P-brains, generically speaking. Like for example, if you have a charged brain and a background field spring that couples to that charge, you can have some external force on this side. So it's not completely general. You can generalize it even more and so on. But that is not so. I mean, now we just stick to neutrals like P-brains. There's also something with you can have rotations and stuff like that. in the transverse directions. But in any case, even in this restricted setup, this has an enormous amount of applications, and that's what I would like to now go to. So, as it's true many times, if you want to see how sort of rich a theory is, you have to restrict yourself to specific cases, because otherwise, you know, these equations are not just easily solvable. So you have to go to specific cases to solve them. So, if I have time, I hope to look at two types of specific cases. So one case is what you call the stationary black holes. So where things do not evolve with time and you have equilibrium, corresponding to the stationary black holes we had in 4 dimensions. That's what I want to do now. If there's time, I also want to talk about perturbations of black holes, where you can actually see some time-dependent dynamics, which illustrates that these equations can actually work also with time dependence and in non-equilibrium situations, as long as you have this machine. So, stationary black holes. So what is a stationary black hole? Well, a stationary black hole, we want it to be a black hole that doesn't have an equilibrium. And if you remember, for stationary black holes, I said at some point that there was this particular killing vector field that characterizes stationary black hole. Namely, it's a killing vector field. I mean, in 4 dimensions, it looks something like this, right? And it has a particular feature that, apart from being a killing vector field, the norm of it was also 0 on the event horizon in 4 dimensions. So, in analogy with that, I will also assume the existence of a particular killing vector field for a stationary black hole. So I assume some vector field k mu, and this is in the background geometry. So that's why I have the index mu. Then it should be a killing vector field of the background. So it should obey the killing equation with respect to the background metric, which we can also write like this. Just another way to write that equation, where you use the covariant derivative with respect to the background metric. And then we want to characterize it such that we only have to use these integrated, these quantities where we already integrated out the horizon. So we cannot immediately write this, because this sort of depends on having an event horizon. So we need to say, we need to make characterization of this which can be formulated in terms of the embedding and so on. So what we do is we say that we look at the pullback of the killing vector field to the world volume. This is the pullback of this vector to the world volume. Okay? And then we demand that this is also a killing vector field, but now on the world volume. So specifically, this means that dA kb plus dB ka is equal to 0. So it's both a killing vector field of the background and of the world volume. But that's not enough. In general, there could be more than one killing vector field that obey this. So we need a restriction that should somehow be related to this one. And that is that the velocity field should be proportional to the induced killing vector field. And specifically, since the velocity field is normalized to -1, this means that we can write it like this, where what we call the norm in this, written in this way, of the killing vector field is this. The minus just because, well, in general, otherwise you don't get something positive. And then I'll come back to in a moment why this is related to this condition, but another reason why this is so, why you take this like so, is that the last two conditions, you know, this one and that one, only concerns the world volume. You can forget about that there is a background geometry. And those two requirements actually precisely characterize stationary fluid configurations. And they're necessary, and the necessary conditions for absence of dissipative effects of the fluid. And I'll come back to that in a moment. But then I also want to remark that if we take this metric we had, I deleted it, but it looks like this. The metric for, you know, for distances much smaller than r, near the brain. Then we can take a look at the background. You know, so this is in d-dimensions. Now we're in d-dimensions, and then we can take a look at how what is the norm of this killing vector field, this background killing vector field for this metric, because we wanted that the norm is 0 on the event horizon, right? So you can see now that if you compute the norm, I mean, first of all, you should notice that here we chose specific coordinates, obviously, for our space-time. So this k mu is actually equal to the induced metric Ka for the first p+1 directions. And then it's 0 for the other directions. Okay? So when we compute the norm, this just goes away. So let's compute the norm. So k squared is g mu nu k mu k nu, and this is equal to. So then we only have to take this part of the metric. So this is gamma a b plus r0 to the n r to the n ua ub and then ka kb, and then then you see the first part here is nothing but minus k squared, right? And then the second part is r0 to the n or r to the n, and then u dot k squared. So now we use this. So if we insert that, then we have, so this is, from this it's k dot k, which is k squared, which is minus k norm squared, but then there's also from the u that's 1 over k from this part, it's denominated here. Right? So we get minus k squared plus r0 to the n, and then this is just also k squared. So all in all we get minus k squared 1 minus r0 to the n. So you see that the norm of k is precisely 0 on the event horizon. Because we chose this. So the existence of such a Killing vector field is what defines a stationary black hole, and it's also a necessary condition to have a black hole, you know, because a stationary black hole, because then it's you have a Killing horizon. So I started late, right? So I have some more time. So now we want to explore the equations we have a bit. So we have these equations. The intrinsic and the extrinsic one. So let me look at the intrinsic equation. And then I want to insert this information and the fact that it's a perfect fluid. I want to insert that into the intrinsic equation. And then try to exploit that it's a stationary black hole that I'm dealing with. So this equation gives me, inserting all this, So you just start taking the the derivatives here, and you use so let me write this. So this is n over n plus e epsilon ua ub plus minus 1 over n epsilon ua ub, right? So you can write it in terms of epsilon alone using the equation of state, right? And then you want to start taking derivatives of all this. And then So I think maybe I should just skip this derivation because it's just going to be very long. Like this. Okay. We do it. So first of all, you should have the covariant derivative of this, but this is a scalar, so it's just a normal derivative. And that gives a term like this. So now I'm just going to skip some steps and then write a little bit. How it's going to be. Then you have some derivative. So you have the derivative of epsilon, where you have the gamma, that is this term here. Then you have the derivative where you have the mu, that's what I wrote here. And then you also have the covariant derivatives of the velocities, and that gives 2 terms more. So roughly speaking, you can see that it gives something like this. Then we can contract this equation with UB, and then we get another equation like this. And then you can insert this result let's see, where do we want to insert it? Yeah, we want to insert it here, I think. So the end result becomes the following equation. Namely that u dot, which is equal to, which is nothing but the acceleration that we also defined in 4 dimensions. So the acceleration of the fluid plus 1 over n plus 1 ua, and then something related to the expansion of the fluid is equal to the derivative of log R0. So if you go through all of that algebra, then you get this result. Okay, so here I didn't use anything with killing vector fields. But now I want to insert that this is given in terms of a killing vector field because of the fluid velocity. So you have that the killing equation. Then you can contract this killing equation.
Something wrong with signs.
There's something wrong with the signs. No, I think it's.
So
right.
the final, there is.
I mean, this one has to go on the other side, so that's this term. So
Okay,
it's
and the
plus.
final answer is u dot plus 1 when plus 1.
Yeah.
Yeah.
Look, yeah, I mean, you have to go through the algebra to see that it's like that. So it's, I mean, trust me. It's more complicated than it looks. To get that's why I don't want to do it. I'll just get it wrong if I try to do it. If you make this contraction of the killing equation, you can show that the norm of the killing vector along the killing field, the variation of the norm of the killing vector along the killing field is 0. And then you can insert this in this expression here with this relation. And then I'll spare you some details here. It's just a lot of algebra. You get that this acceleration can be written in terms of the derivative of log of the norm of the killing vector. It's not difficult to see that. Then you can also see that from this equation you have that dA Ka is equal to 0. So you can say that the expansion of the killing vector field is 0. Divergence, whatever you call it. Staring a little bit at this part here, you can see that this part disappears for that reason. So all in all, what you get from all of these considerations that the variation of the log of the norm of the killing vector field is equal to the variation of this R0. So that means that R0 over the norm of the killing vector field is equal to a constant on the brain, on the world volume of the brain. And this might very well mean nothing to you, but it's a very important result. To understand the meaning of that result, we have to be more specific with what killing vector fields we are choosing. So yeah, maybe I should save that for tomorrow because it's a longer story. this will, I can say the result of this. This is related to having to the zero flaw of black hole thermodynamics, saying that the temperature should be constant. So that's what this will end up showing. And yeah, so okay, so I'll explain that tomorrow. Okay, so are there any questions before we end? So, or is everything crystal clear? Oh, that's good. Okay, so thanks.